papers, but nevertheless, I wrote my very first one with the title, Why TCP Timers Don't Work Well. Why I wrote the paper is not because of pressure, but because I really wanted to get this question answered. Back then, I was never a decent system programmer, so I couldn't contribute much to the early days of TCP/IP development. But I heard the people running in the hallways and complained about TCP timers really sucks. It either timed out too early, otherwise too late. Either way is great. So at the time, the TCP timer setting was look like this, as I shown on the screen. It's later that Van Jacobson fixed it. But given the setting algorithm, a number of papers actually published trying to tune the parameters, the alpha and beta, in various ways to see, can we make the TCP timer work better? But everyone knows there's really just a dilemma. You tune it one way, it times out too soon, and tune in a different way, the timeout is too late. And in particular, there are different environments that you can just never get the parameter right. I figured that I'm not that great with tuning the algorithms. Let me understand why it doesn't work well. I feel that the timer goes off at the wrong time with the symptoms. There has to be a root cause. So I went around and talked to people, collected the reasoning. And to me, like I said, rather uneducated person, I try to understand the issues from the intuitive sense. I figured it's obvious. It cannot work that well because there are many random variables affect the round trip computation. And the sender, meanwhile, had a little clue what's going on. So it doesn't matter how you adjust the alpha and beta, you cannot win. So I really learned a lot from just writing this paper, collecting the ideas from others. Essentially, the hosts are blind, they cannot see like we do. And so therefore, you need a timer to trigger retransmission when nothing happens. But nevertheless, you really cannot depend on it for performance tuning. How you can get a better performance, get more information, so that the host can make an informed decision. So meanwhile, the lab actually started another project that's very much related. So therefore, whatever I learned from here, I get applied to there as well. So this new project called NetBlade, Network Bulk Transfer Protocol. The goal is to achieve high performance over high delay, high bandwidth, and also very lossy channels like the satellite. So observation shows that the bandwidth is high. Well, when we say high, this is kind of a few megabytes per second, if I remember, but that was pretty high at that time. The problem is not so much how many megabits per second you can receive, but rather the achieved end-to-end throughput was way, way below what the bandwidth was really is. So I kept this notion asking for root cause. Why can't you blast the transmission at the link speed? So this is a more complicated issue than the timers. So how can I see things through? I apply the heuristics. I say, let's think about extreme conditions. What if the channel has no losses? If there's no loss, delay doesn't matter, because you just pump the bits into the channel from one end, it shows up in the other end. But of course, with the losses, now everyone knows there is a transport protocol state that keeps track of the sender, keeps track of which one received and which one not, and then you have to retransmit. Okay, now we learned you need a state, but state wasn't an issue if there are no delays. Why? Because without a delay, the receiver and the sender can be perfectly synchronized with regarding to their understanding of which packet get received and which packet get lost, and you can just retransmit instantly utilizing the full bandwidth. But unfortunately, delay exists. So what that means, the two ends, especially the sender, couldn't really know which packet get lost and to figure out how to do the retransmission. And it is that kind of sorting out what's going on that halted the transmission. Now, given the emphasis on the high throughput, so that means that the transmission has to keep going independent from all the losses. And one can see very clearly who knows better about which packet get lost. It's not the sender, but the receiver. So NetBlade design decided, let's make the receiver to be in control. Assuming that the sender transmits at a constant rate and the receiver learns everything by just watching the packet arrivals. You can see how the delay jitter distribution looks like. You can see how much the packets arrives out of order. And this really avoids, by and large, all these retransmissions, unnecessary retransmissions. So the receiver just requests the missing packets and sender just plug them into the waiting queue of the data, all the data that's going out. So this way, NetBlade really achieved the throughput that hasn't been achieved before. Now I learned something more. So that if you want to better understand a complicated problem, consider the extreme case. That really kind of shows the insight more clearly. And this notion of having the receiver to be in control gets stuck in my head. In the early days of internet, there's so many things to be designed. So I figured I'm gonna use the same idea for other protocol designs. And indeed, opportunities for design was a lot. So soon after I graduated and joined the Xerox PARC, at that time, there was a little testbed called the DARTnet, DARPA network testbed, connecting about, I think, just a dozen different places. They're using the routers of the workstations with open source software, so everyone can play with it. One of the early things people tried was that doing a bake-off of different scheduling algorithms. Rock mentioned about virtual clock, that was one of those things. But you can see that to testing different algorithms, the scheduling algorithms, that requires that, when you try algorithm one, you set the router control in one state. And when you test the next algorithm, you have to change your control state. There's this fellow called Andrew Haibai. I still remember his name. A research assistant from MIT. He dutifully sitting there and log into every router to change the control state when the bake-off went on. And also I remember Dave Clark half-jokingly said, "Hey, Lixia, maybe you can make an automated Andrew." I said, "Sure, I will do it." And that's the start of this protocol, R3P. So first thing we realized, the network actually needs state. So how this goes with stateless networking? I think both are correct, because here the state is not the end connection state. So this is really the network state. Like I said, I applied my receiver-driven approach to say that it should be the receiving end that decide how much I want to reserve, and etc. But how would the receiver's reservation request get to the sender? Because routing goes in one direction from sender to the receiver. To get the receiver's request towards the sender, we figured out we need to do a two-way signal message exchange. The sender first sent, they call it pass messages. Then the receiver's reservation request can just traverse the path set up by the sender. But you can see that this two-way message exchanges really close the feedback loop. So therefore, you actually know whether this reservation is in place or otherwise not. I think I learned is another thing, that is the feedback loop. It's an important thing to design into your protocol. Another question is when the receiver sent the request, exactly what you want to put into that bag of bits that are going to be dropped at every router to set up the state. So although the original intention for RSVP was really for resource reservation, we were thinking about supporting real-time applications. But nevertheless, we decided that the protocol itself should just have the notion of carry a bag of bits and not defining what's in the bag. And that turns out to be really the right design decisions. And of course, this reservation, because we're thinking about the real-time applications and the conferencing like we do today, was really important consideration. So we made the RSVP to support both unicast and multicast. Well, the word multicast might get some people raise their eyebrows. Well, I'll mention that a couple of slides later. But I want to also point it out that I think this design turned out to be pretty good. And I need to thank my co-authors. Look at the names. That's all the first-class researchers, and I was just so fortunate to work with them, get this work out. There's Steve Deeren, Deborah Estrin, Scott Shanker, and Daniel Zapala. So I learned a lot from doing this development, building the feedback loop, and less actually is more. That is not define the content of the bag, but just letting the protocol to deliver the bag drop off at every routers. And after that, I remembered it was Bob Braden from USC SI who actually helped take this design into the IETF, made it an internet standard. And after that, the protocol just moved on with a life of its own. Rock already mentioned, to get deployed, redeployed, revised, and used in many different ways that I never thought about, like setting up MPLS pass or even the optical transport pass state. So when I was preparing for this talk, I was curious, is the RSVP still used? So that I had a look, and I was amazed that just a quick search to Google to say, internet draft related to RSVP, and a bunch of them showed up. That is the protocol after 20-some years is still very much actively in use. I just grabbed this as an example. There are a number of others that currently still people are looking into the usage of that. So another thing I want to point out is that you look at where the paper came out, it's not SIGCOMM. I want to tell you the truth that it wasn't that we didn't want to submit to SIGCOMM. Actually, ever since my first few papers went to SIGCOMM, it became a habit that submit your work to SIGCOMM to share with others. Just unfortunate that this paper submitting to SIGCOMM got rejected, because if you look up SIGCOMM 1993, there's a bunch of excellent papers. So therefore, this one wasn't up to date. But Craig Partridge, if I remember correctly, actually noticed this paper and said that this is a pretty good paper. So if you are interested, submit to IEEE network. And so we did. And years later, when IEEE Communication Society celebrating their 50-year anniversary, they picked 10 landmark articles, and this became one of that. I mentioned this anecdotes just to say that next time when you have a SIGCOMM paper submission rejected, don't feel too disappointed. Maybe paper will find this way elsewhere. So let me get back to my promise to talk about IP multicast. I save my time to make the slides. I again Googled, and Google turned me this picture to illustrate how multicast is a great idea, right? You know, you do unicast, you have to send many copies of the same packet. You do multicast, the router will do the job. So the great idea, efficient data dissemination. This is what people really paid attention to. The second great point about multicast is about information discovery that I think people didn't draw as much attention as the first one. Why this second thing is important? Because there are many times you don't really know exactly which IP address you want to send your packet to. Like here, if I ask, what is the time now? I don't really know who actually has a watch. There's yet another important effect for doing multicast. I think there wasn't listed here. I noticed some errors. So this actually described in the RFC 1112, not 1122. And what the RFC 1112 says is the host extensions for IP multicasting was written by Steve Duran himself. So at the basic side, how you create a multicast group, let the host to choose themselves. Again, this is just echoes back to the earlier concept, communication. It's better to be receiver driven. And with that, you get this third advantage. That is, I don't get any packets that I didn't ask for. If I don't join the group, nothing from there gonna be sent to me. And this is, I think, really important. You know, multicast really created kind of enthusiastic efforts in the research community. So many people jumped into it. I think a big chunk of the effort went to how to support multicast routing the packet delivery. Meanwhile, I actually got attracted to Vance Group's effort to see how we can utilize multicast to enable new applications. Before I tell you the story of what kind of new applications we tried, I have to mention another seminal paper by my former advisor, David. So David Clark and David Tennerhouse had this fascinating paper back in 1990. Again, of course, on the SIGCOMM. The title says, architectural considerations for a new generation of protocols, but I tell you, it's not like what we talk about, a new protocol design. It's actually tackled one specific question, that is, how you can make the host run fast in packet protocol, the packet processing. They looked at the current protocol stack. You notice that we still do that way. That is, every layer put its own header, so therefore it needs its own processing, process the header. This ended up with a situation where packet, upon reception, you actually have to move it in out of memory more than once for each layer to do its own processing. So again, intuitively, of course, the way to fix it is that you only read the packet into memory once. And how can you do that? It requires that you actually package the packet with some application level data unit. So this was called application layer framing. Then once you receive a packet, you put into memory, you can do the processing of all the multiple layers at the same time. And that is adopt integrated layer processing. Of course, this idea actually is a great idea. The paper got cited many, many times, but it wasn't really implemented in current practice. Nevertheless, since we have this protocol called UDP that does nothing but just give it bag of bits, it's going to send it out. So therefore, UDP is a convenient way you can actually utilize the concept of this ALF. Then this new application, the new way to develop applications led to another SIGCOMM paper. It's called the Reliable Multicast Framework for Lightweight Sessions, blah, blah, blah. And Van Jacobson himself gave the talk at the SIGCOMM 95. And I just copied the few slides out of his presentation. So, ever since the ARF came out, we tried to see whether it's a great way to make use of that. And one way is to combine the ARF with the multicast delivery. So we dubbed this term called the Scalable Reliable Multicast Framework, SRM. I think many people, if you're old enough, you probably remember SRM. Because it's utilized multicast to disseminate data, and therefore is completely decentralized. And one application tried as like a driving kind of a case study to understand how you make this protocol work well is distributed whiteboard. I put a picture here. This picture is not from Van's talk. This actually, as you can tell, this actually is a distributed whiteboard application implemented over NDN. But I just want to use that to illustrate the point, right? Distributed whiteboard, you write on one, all the other devices in the same application group gonna receive it. So this requires reliable multicast delivery. Now, how does SRM do that? The spirit is that everything goes multicast. Whoever has data to send, you just send it. And then meanwhile, all the members in the same multicast group need to send this kind of a low rate report, that is tell everyone else what packet I received from which other participants. Why you do this? Remember we said earlier, this is the way you actually inform each other about your end transport state, rather than keep everyone kind of in a blind guess which packet get lost or which one not. This explicit information will make the receivers being able to quickly recognize if it's a missing packet. And then rather than waiting for the timeout, you can see that the same idea I learned previously got really reconfirmed in the new protocol design. So if someone notices that there's a missing packet, you're not asking the sender to send it, but rather you just yell out, hey, I missed this packet, and hoping that whoever nearby can send you a copy. So here comes this very important notion. Today we do networking. It's always the sender sending to receiver. But SRM really promoted this new notion, that is, communication is not about conversation between sender and the receiver. Instead, we're really disseminating data. So therefore, if someone misses the packet, anyone else has the data can just help out. You don't have to wait for the single sender to handle all the losses, because in the big multicast group, that just won't scale that well. I noticed that I need to move forward a little faster. So we solved one problem, that is the retransmission doesn't have to come from the sender. You can yell out and everyone else would be willing to help. There's another problem introduced by this notion of group help. That is a crying baby. So think about the link between the R2 and D is a lossy link. Then the D just would keep sending this repair request. And that's gonna propagate to the entire group. It's not great. So we, several others you can see from the cited reference tried hard about, can we constrain this recovery into a local scale? We tried really hard. But I honestly tell you, there's simple solutions. Now, again, apply my thinking that these difficulties of funding the local helper is only the symptoms. What are the root causes? So you think deep, they're going to push you to understand now. That is, yes, multicast allows you to not naming specific nodes to send you the packet, but nevertheless, the multicast still just identifies a group of nodes. It's not about knowing that what carried in that request is, hey, I'm looking for a specific data packet. And therefore, router basically dutifully send your request to everyone in the group. And there isn't really any sense of, oh, this one's closed, like here, the host C is closed, we can just go there. Router does not have that concept because we just deliver to the nodes and we don't know who has what contents. Contents is out of concern of the routers. Another question you really notice that, you know what, all the packets go through all the routers. So that if C got a copy, the R2 should have seen a copy earlier. Why can't the R2 help? And this is because IP, including IP multicast, this is about packet pushing. It requires this synchronous communication when everyone's online. The router, although it has a buffer, it doesn't know what's in the bag. So therefore, it cannot keep it because the duty is just to deliver to where it should go. So you get stuck. Honestly, you know, I thought about this problem. I realized there's no easy solution. Then, meanwhile, there's another thing that gets started. So at the same SIGCOMM, SIGCOMM 95, there is a workshop called the middleware workshop, and I was asked to chair a session on something like a high-level communications. And of course, I invited, you know, the no names. One of them is Van. In those days, there isn't much of the conference material preservation. So most of the talks is no longer online, but fortunately, Van's talk was still there. So whoever interested can take a look. The title of his talk is very attractive, say the least, called How to Kill the Internet. So the internet was designed to be robust, resilient. How man might kill it? Easy. Invent the web. Why is it so? Because web in those days just overwhelmed the network. One has to remember this was back in the mid-90s. It's a pre-CDN days. So one basically said that we cannot do this, you know, many-to-one client-to-server connection. To scale, we have to explore the utility of in-network caching. Again, this is all just directly copied from Van's slides. So data has to find the local copies rather than you go all the way to where the original producer is. Remember, we're seeing this idea actually earlier when we talked about the SRM, the repair also could have come from nearby nodes rather than always from the original source. So how you can do this? You know, close your eyes, you can imagine that it can build this kind of dissemination tree rooted to the source, the web server, and just as the data got put out of the server, it will be kind of left the copy along the path, and whoever else comes along later, you can grab a copy. And this means that the browsers cannot just send the request to the server anymore. Instead, you just ask it to say, hey, I need this HTTP objects. This sounds a very exciting idea. So right after that, I joined UCLA, and among my first projects, we decided to do this called Adaptive Web Caching, or ARC. It was founded by, I remember it's Hilary Allman from DARPA. And this is directly out of the presentation we gave to DARPA to say that, hey, let's design this scalable and robust cache system. Just like IP. IP is simple, scalable, robust, delivers packets in a transitive way, all the routers forward the packets to the destination. So why can't we do caching in this way? Just that the request goes the opposite direction from the browser to the server, and then the global caches gonna do the transitive forwarding and get a copy to everyone, solve the problem in a beautiful way. So then, you know, in those days we give talks, a few still hanging there. If you want to take a look, we wrote papers, we built a demoware, and not many people knew about it. The students actually put off a startup and got big funding from venture capitals. With all of this, the design actually ran into a stone wall. Why? I think it's pretty clear, right? So what we wanted is a generic cache overlay that runs over IP to support all web traffic. It's not about web proxy that only attached to the browser, because there'll be lots of such proxies. If they talk to the server directly, it doesn't solve the problem, solve some problem, but not to the degree we wanted. This is not about the CDNs. That's how we rely on today in doing the delivery. But the CDNs doesn't really cache my traffic. I remember vividly showing this picture was about 10 years ago when iPad just showed up. And at the time, I think Obama gave a talk somewhere. As he walked off the stage, multiple people asked for the autograph. And I saw this news one evening from the CNN. It says that, you know, Obama politely just declined everyone's request except someone handed him an iPad, you know, like I show you here, to say, Mr. President, please sign my iPad. And Obama smiled and actually signed it. I thought it was pretty interesting. The CNN said that here is a link to that video clip. I clicked, it didn't work. I got back some error message saying that the server busy or something like that. This is what I meant. That is, you wish that on the internet, just like you have connectivity, you should be able to also do scalable your data dissemination without having to pay the CDNs to do that. None of us actually can afford that. What the difficulties? It's really hard. We tried all the smart ideas, but utilize the multicast. It's just so hard to make the caches interconnect, discover each other, create a global overlay. It's really hard to grab the browser queries. If you don't want to make changes, configure as like the ARC cache as like a local proxies. And you really don't want to, and you cannot reconfigure all the browsers. And another thing is that it's hard for the caches to figure out where the content really is. So if you think about all of this, it would be really easy if this were like a network layer intelligence. So the root cause is very much clear, right? We don't do networking by the content names. And if we do that, then that would also help solving all the SRM problems that we identified. But this notion, you know, you're looking back, that you do networking by content names sounds like a blue sky thinking. So after that, I just dropped the ball, and then I went on to focus on the global internet infrastructure challenges. So by 2006, when Van gave this great talk at Google, a new way to look at the networking, I actually missed it until like a few years later when we met each other at the NSF meeting. I think NSF was about starting the Future Internet Architecture program. And Van said, here's a new paper and take a look. How about we work on this one? And the light bulb just went on. And this solved the problem that we struggled before. This talk not mean, I won't have time to give you a NDA introduction in any detail. I remember Craig Partridge said many years back to say that the great talks are not about explaining all the details, but you can raise enough interest from the audience so that they would read your papers on their flight back. Of course, nobody flying this time, but I hope to give you some basic idea to raise your interest that you're gonna look into this later to learn more about NDA. The idea is very simple. You know, for IP, everyone knows the one just shoot packet to the destination address. And the NDN is like the figure shows, right? You send a request for data, we call the interest, and data will just come. Where the interest goes, you leave to the network to decide. What do you carry in the interest? We say name the data, so you carry the names. Many people ask the question, where do you get the name? And I want to show this example that we already have the name. We already have the name. And if like the YouTube thing is too big, then you just chop it into segments and you still name every segment. So every piece of NDN data has unique names and also is immutable, but I'll mention that later. One thing I think is really important to clarify, NDN is about semantically meaningful names. It is not about human readable names. Human readability, i.e. ASCII encoding, that's an encoding question. That's not a naming question. The question is about however you encode the name, is that semantically meaningful? And that is the essence of NDN names. So we see that IP has one header. Now, NDN need to have two different packets. One is requires data, and the other carries the data back. So therefore, both packet types must have application names in it. And in particular, you want to notice that for the data name, it also carries the signature. The crypto signature binds the name to its content. So therefore, data gets secured directly. This doesn't mean to say that you cannot run TLS. Of course you can if you want. Okay. It's just that the data will be secured independent from whether the container of the data is secured or whether your communication channel is secured. That is really an important property. So the question is now, look at this, right? It only carries the names. Where did data go? For the interest, we'll say that you know, you can build a FAPE for all the content names so that router will forward the interest, just like forwarding the IP packets based on the FAPE, except that the NDN FAPE will contain the name prefixes instead of IP address prefixes. But that's not enough because the request doesn't really say who sent this request. So therefore, to get the data back to the requester, there's a few other pieces were added in. So the important one is called the pending interest table. Every time you send a request, you actually need to remember that. You remember the incoming interface, outgoing interface. So therefore, when the matching data with the matching name comes back, you send back to the incoming interface of the interest. And then you can just opportunistically save a copy in your content store in case other requester can come along asking for the same data. What's the forwarding strategy? That's a decision box, but let me mention that later. So that this whole thing, either your IP or otherwise NDN, is really just the narrow base of the protocol stack, but implemented in very different ways. You know, one side will push packet, the other push packet to destination, the other side will actually fetch named and the secured data. People may say that, you see, the NDN nodes is way more complex than today's IP router, but I want to tell you that that's actually the opposite. What's in the NDN nodes, I showed you here. What's in the IP router today? Well, you can read the RFC's internet draft and figure out how many other things that all set up the state at today's NDN router. There's MPLS, there's VPNs, there's a multicast, and a bunch of other things. It's all try to kind of enhance IP routers to do the delivery better. So what NDN is doing here is just that thing, deliver the data better. But it doesn't have gazillions of tables. It has one table. It's a pending interest table that does the job for the MPLS or the VPNs or multicast or other things. And I just want to say a few words about this pending interest table. You know, of course, here we see the same thing like you've seen before. Anyone that has data can reply. You heard this many times now. And data is secured so that you can do this because it doesn't matter where data comes, you can verify it. This is stateful data plane, I think puzzled many people. Why you have state? State is a bad thing, isn't it? This is a brand new state. I want to explain that. This is about the datagram state. That is, you send the interest as a datagrams. You merely just keep track of that fact. You receive the interest so that when matching data comes back, you can send it back. So this is still datagram. And now you learn that datagram can have state as well. Why you do this is because now you can do multicast. You can receive multiple requests for the same data. Only one is forwarded. But when data comes back, you send a copy to each of the interfaces that the interest came in earlier. Now you can do multi-pass forwarding. The challenge of multi-pass forwarding is routing loops, right? You send data along multiple paths, some might come back. For IP cannot know. IP is a stateless forwarding. You see the same packet 3 times, you forward it 3 times. But for NDN, because you actually keep a copy of your interest in the pending state, you can notice the loop and therefore you eliminate that. So therefore you can free doing the multicast forwarding. And then there's the flow balance, there's congestion control, there's a fast adaptation to failures. How you do all of that? It's because of a pending interest table. You know, when you send the data, interest, you get data back. That is a closed feedback loop. And with that, you know how the path is working. If you want to do flow balance between different paths, you can do that based on the observed performance. And if the failure happens, you know that. You send interest down a path as expected, but if the data doesn't come back within the expected RTT, you immediately can try alternatives. So I want to be the first one to admit before you ask the question, how big will be this pit? And if you forward the interest based on the names, how big is a FIP? It can be big. I'll just mention 2 things. One side, we have thought about those problems and provided the solutions. But the one thing, remember very clearly, I mentioned yesterday, today we have abundant computation, abundant memory, abundant computing resources. So the question is not so much how you build the most efficient forwarding plane, but rather how you can fully utilize all these abundant resources to provide the best service for the applications. I see I'm running out of time. I want to just give more pinch to the security aspect of the NDN. People tend to think that the NDN abandoned the end-to-end principle. Actually, I think NDN enhanced it. That is to say that now data is secured by the producer. So therefore, when it moves inside the network, security goes with it. So why the data stops between the sender and the receiver? For many reasons. We said the resilience. So therefore, you don't really have the consumers talking to the server directly. There is the mobiles, and there are delay tolerant networking scenarios. So therefore, expecting a direct pass, a physical pass, is just no longer the reality. And with the NDN, it doesn't really matter how many stops you go in the middle. When the data reaches the end users, you can always do verification. So for more details, we have this an overview paper on NDN security one can look into. So let me just summarize. So the essence of networking is about delivering a bag of bits to applications. So the fundamental question is really, what's the namespace the network use? And NDN in that regard fundamentally made a change. We say that let's not name the nodes, let's name the data and fetch the data by the network. Secure data directly, and we build a stateful forwarding plane. Looking back about the principles mentioned earlier, I learned from day one. NDN is still datagram. And NDN actually enhanced the end-to-end principle because now we have end-to-end security. Again, it's a fully distributed. It's not as a necessity, but as a great capability. So people ask questions about how you can roll out a new architecture. IPv6, after so many years, I think we still face the challenges. And I will just say this way, that is, replacing IPv4 with IPv6 is a fundamentally different story compared to how IP actually replaced telephony, that is run over the top. How do you get a new architecture out? IP told us, that is, if you just have your own applications, you have running code used for apps, then the protocol will walk out on its own. And that's what the NDN is trying to do, so that we have developed a number of NDN apps. You can call it the demowares. And I want to mention one of them. This is one actually done by people from Memphis. This is about NP Chat, a multimedia sharing application. What I quoted here is a news article. It talks about to say that in a world dominated by big internet players, the NP Chat really make a nice alternative, so people should look into. Why is worth looking into? Because look at these properties. There's no central control, no single user directory, no special infrastructure, and it's user-controlled data. So there's really the real running code, and people can take a look. I want to say that this NP Chat really represents one of the many applications we have tried. The common features is that it's pure peer-to-peer with the security built in. And even when we use the NDN to solve new applications, it was really pleasant discovery that for applications back in 2010 we didn't think about, NDN seems to be ideal fit. I think this is because NDN grasped the essence of communication. That is, it's really data-centric applications that requires a data-centric delivery subsystem. And NDN empowers end users and facilitate distributed applications, like I showed you as the NDN app, the NP app. I want to particularly mention about this last point, about developing distributed applications. Because look at today's world where we are. And I would just want to cite another thing I received over the weekend when I was preparing for this talk. So, Jeff Houston sent me the pointer for his August blog, and read his word. I just picked 2 sentences out of his blog. It says, it's truly amazing that the sum of human knowledge is at my fingertips, instantly accessible from anywhere at any time. It's incredibly empowering. At the same time, it's truly threatening that all this information is only accessible through a single entity. Who funds this service is through an insidious economy based on surveillance capitalism. It's a very much thought-provoking statement. I'll just leave like that. So I'm running out of my time. Let me sum it up. I think I promised too much to say I'm going to tell you how to learn the art and the science in the practical designs. But actually, what I have, I look back, I just collected a bag of tricks that I believe could be useful when you design your next protocols. Of course, you use timer right. You think about the soft state, feedback loops, and try to see whether less would be more. There's a few other things I didn't get to talk about, like a slow start, randomization. But the last one I want you to remember, whenever you see a problem, do not just solely look at how you cure the symptoms. Try to find the root cause. Try hard to find that root cause, why. That is how I got to get a deeper understanding of the network properties, and see where the future should be. And I hope that that understanding can also help you to see the problems better. So, this arts, as I said, it's overpromising, but I want you to remember the last bullets, finding the root cause, always. Okay, now, where's the science? I think, again, I overpromised. But let me bring up this question. So I've heard it so many times, is networking research a scientific undertaking? And my answer is, let's look at the other scientists, like a physicist. What do they do? I think their job actually is way simpler than us, because whatever you call the nature of God made the world. All they have to do is to interpret it. And for us, it's fortunate or unfortunate, we don't have a given world. God didn't build the internet, and there's a Bible to study that. But it's fortunate so that we got to design it. So once we have the artifact, then we do exactly the same thing like a physicist. We do experimentation, we draw lessons from the practice, and the lucky part of us is that we can change the design. And then after that, of course, you repeat the scientific process cycle. I want to point out that, we're going through the cycles frequently for incremental improvements, but we do go through the cycle infrequently for architecture changes. And to make a scientific spin on that, in biology, this is called punctuated equilibrium. It says that after a prolonged time of incremental improvement, then you will have disruptive changes to move the evolution into the next stage. And then I think networking, now we are facing this next architectural punctuation. So after that, I will just leave you with these slides. That is, we had telephony that built a circuit. We have the internet, IP, I would say, pushing the packets to destinations. Now we recognized that the better way to do support the internet today is actually moving into this data-centric design, name the data, networking. So focus on fetching named secured data. So that's the end of my talk. Thank you very much.